So I'm going to just review some of the basics of constructing models for CFD, and hopefully this will maybe be a springboard for us to think about the process and where we need to go. So to begin, I quite like this image. I suppose it's a standard joke, but if we looked at how we actually start to view the nose and how we start to view the process of modeling airflow in the nose, we would start with, how do we define the model? This is the basic of all engineering modeling. And then when we've done the modeling, we need to think about, well, how do we check? Is it any use? So we have to talk about, what is, if you like, the quality assurance we've done in producing this model. Have we done our homework? Have we validated it? And then finally, I think we need to think about, well, what's it worth? So we need to have a process of evaluation of the model. So in terms of defining the model, we have to think about, well, what areas are we interested in? How big should our computational domain be? I mean, ideally, I suppose the clinicians would say we want you to cover everything, but we're not at the stage where we have generally computing power or data allowing us to do that. So we can't do everything. We have to be quite targeted in the areas that we decide to model. And then the next stage is the process of defining what the airway is, segmenting the airway from images, whether they be CT or whether they're MRI. After this, we have to define the boundary conditions. By this I mean, what is the flow rate? What is the inflow? Oh, I've just pressed the wrong button. What's the inflow and outflow conditions? What is the temperature at the surface? What is the capacity to humidify? Having done that, we have to decide what the solution method should be. What parameters are we going to set in terms of achieving the solution? Then finally, we decide how do we choose the mesh time step. I put choosing the mesh last because that's very dependent upon whether we want to use conventional methods or maybe more possibly future methods such as lattice Boltzmann methods or Cartesian based modeling, which offer some possible advantages. Then briefly looking at validation and convergence in terms of quality checking, and finally our evaluation. Well, how sensitive is our model to various parameters, and ultimately what's the benefit of this? So in terms of the region of interest, as I say, we would like, I suppose, eventually to be able to model everything, but we typically decide, well, we're going to just choose to model maybe just the nasal airways, maybe just the trachea, but in which case we have to then consider what's the impact of the region we've cut off. Now, in fluid mechanics, because we're dealing with an internal airway, generally what happens downstream has little effect. So that's okay, but what's upstream has a big effect. So inhalation generally is much easier than exhalation. Fortunately for us, often that's where the problems arise, because in exhalation we have to think about what's coming all the way back up from the bronchi through the trachea and that. Whereas inhalation, we just have flow coming from a simple sink flow from outside. So having decided then we're going to fix a particular region of interest, we then have the process of segmenting the airway from images. And I'm afraid this is certainly not an automated process. It's really the challenge of this, I was going to say horrible geometry, maybe I should say this wonderful geometry. These very fine passages and the limitations of current imaging technology means that it's not possible really to do this reliably without some degree of user intervention. That level of intervention depends upon the imaging modality, and it depends upon exactly how much of the airspace we want to include and how accurate we wish to be. So because this is not a precise process, then there's uncertainty in terms of the geometry. What is the geometry? There's uncertainty, as Dr. Shetto has mentioned, not just what I'm talking about because of knowing where the boundary is, but also because of, well, what was the nasal cycle? What are the tissues doing? Let alone in terms of the dynamic airway. So there's myriad uncertainties. And there's also uncertainties in terms of the flow, because each time we breathe, it's always different. We never breathe exactly the same way. And so there's a whole variation in how we breathe. And we need to be mindful of these things. In terms of defining the airway surface, then we start off and we have to define what the airway is, but then comes a process of smoothing to make it into something which represents the natural smooth surface of the airway. This can introduce some other uncertainties and some other artifacts, so we have to check against the original segmentation. Following this, we have to define inflow conditions. So the best source for this is actually to look at what happens in practice. And we can look at experiments. And there's a difference between measuring flow when the nasal alae are forced open versus when they are free to move. So that's also an important characteristic, to look at what happens when we allow a free breathing, maybe with a mask or maybe even without a mask. And then we think about, well, what is a representative breathing cycle? So here are just some of a few traces from an individual, and we've looked at this variability, and we see that there is on average a certain characteristic, but there is a huge range of different ways in which people can breathe. And this is something which I think has yet to be explored. Well, if we decided we take the simplest case, we would just take a steady flow approximation, then we have to decide, well, what is the appropriate steady flow? Are we measuring flow as a sort of an average? Or are we measuring it at the, if you like, the plateau phase where there tends to be a period of more rapid inhalation? So what is the appropriate steady flow? Again, more uncertainties. Or we may decide actually we want to look in detail at airflow as a dynamic condition, in which case we're looking at maybe the time rate of change of the inflow profile. In which case, if we want to look at this and make sure we are capturing everything, we start to think about this as maybe a task for a supercomputer at present. But you know, supercomputer of the present is just the future mobile phone. So we have to be aware of how quickly technology is advancing in this area and not be shy of the possibilities this affords us. Then comes the case of choosing what is the appropriate solver. So we have a choice between commercial codes. Most of these are boundary fitted codes such as STAR CCM+, ANSYS. There are various other ones. And the advantage of these are in terms of the support they offer, the fact that it's very easy to tell your student or someone to just read the manual, look at the myriad online documentations. So that's a big plus for commercial codes. Also, they have very broad capabilities. They're now at a stage where they incorporate many, many physical models, so that's another advantage. Mesh generation generally is more straightforward, but there's an issue of cost. So what are the alternatives? Well, there are open source codes. For example, OpenFoam is one of the popular ones. The advantage there is these codes can be hand-tuned. So you can hand-tune them, you can embed them, if you like, in something you want to develop. But you have to bear in mind that generally they are less capable. It's up to you to add extra features you wish to these, and they will have less support. And then there are newer alternative methods, such as lattice bolt methods or Cartesian-based methods, such as in Compact 3D, which in some ways they avoid the issue of complex mesh generation. You can't get away from the issue of defining the surface, but that's separate from defining what the interior airspace should be discretized as. Now these have advantages, possible advantages in terms of efficiency, because they're by nature very easy to render parallel and very suitable for high performance machines. But as yet they are not quite at the level of boundary fitted codes. But I expect this is an area which may change in the future. And so also these have generally less implemented capabilities and less experience of these. So then we come to defining our mesh resolution. And if we were to use a novel method, it would be how many billion cells we have in the interior. If we use a conventional method, it would be maybe more like how many million cells as opposed to billions. And there's an important consideration there, and the consideration is, what difference do highly resolved simulations make? Here we see this is a very, very highly resolved simulation, certainly not as highly resolved as the sort of simulations that Dr. Kamel is using. He will pour scorn on these very crude simulations. But if we look at the difference, for example, this is flow in the trachea between highly resolved flow with a very small time step, and what happens if we reduce the number of volume elements and use a coarser time step. Well, of course, this has an impact on this flow solution. Now, the magnitude of that impact depends upon what is the question we're interested in. Are we interested in exactly how particles move in the airspace, which is a complex area, very highly dependent upon the turbulent structure, or are we just interested in maybe an energy cost, an overall pressure loss? So this is an important consideration we need to be aware of. This one is chopped off, but it doesn't matter. It's probably better chopped off. It's just showing the impact of time resolution. So I mentioned it depends upon where we are in the airway, what the question is. So, for example, in this case of a complete inhalation cycle, we see there's a huge difference between the level of flow and steadiness in the glottis, where we have a highly turbulent jet, and in the nose. And this is for quite a high flow rate. So in the nose, we see a much lower level of disturbance, and so we can use less exacting methods for the nose. So then, in terms of I suppose some of the basic considerations in terms of applying CFD, the things we need to be thinking about. Next comes the idea of how we check the quality. And I quite like this image. I don't have the copyright for this, so be careful if you want to publish this. But if you look at this very carefully, you see there's a difference between what maybe the CFD developer is producing and what the end customer is seeing. So they may be promising something, and then you're actually seeing something quite different. So this is something to be borne in mind. And we tend to shy away from things like quality assurance and that because it seems quite boring. But actually, really, this is one of the most important issues we need to be constantly aware of, particularly if one of our students is ending up going to operate on us using something we think we've developed. So these are some considerations we need to be very much aware of. Well, these are techniques where we occasionally we can answer some questions just in terms of the raw CFD by doing these very expensive model-based measurements where we translate a physical geometry into, a virtual geometry into a physical model, and we do continuous particle image velocimetry. Well, of course, that's not practical in most cases, nor is it necessary. It's good to have done it a few times, and it's good to do it for new cases if we want to look at more complex cases, just to be sure that our computations are sufficiently resolved. But what I think is important lesson for us is when we produce models, computational models, always we should provide enough detail in what we publish to enable others to check our methodology. And sadly, that's not always the case. And we should always give some information in terms of what convergence checks we have performed, how we validated at least our model. Our model probably is very imperfect, but how can we give other people confidence that we've actually thought very carefully about the physical assumptions and constraints and translated these into a model we can be confident in, confident of. So finally, in terms of evaluation, and this is where I shall wind down rapidly, the question then is really how do we look at what it is we've produced? And in this case, I'm just wondering what side of the mirror are we? We hope we're on the right side of the mirror rather than on the other side of the mirror. But this is something we need to be careful of and be honest in terms of evaluation of what it is we've produced. So in terms of evaluation, what I would like us to reflect on in terms of what is the aim of modeling. So if we are interested in basic physiological processes, I would say that's far less demanding than if we are purporting to do patient-specific modeling. In the case of physiological understanding, and this is where a lot of what we've been doing has been based, then we don't have to be so precise in terms of representing faithfully an exact geometry. As long as that geometry or those conditions are broadly representative of what species it is that we're modeling, then that's enough to inform us and provide very valuable insights in terms of making us aware of what may manifest itself in terms of a pathology, or what the ways of managing that pathology may be. However, when it comes to patient-specific modeling, there the bar is that much higher, because now we are purporting to say, well, for this particular geometry, first of all, that's the geometry you've got, or that's representative of the geometry you've got for most of the time. This is the prediction of the CFD which I have produced for this geometry, but what is the level of sensitivity to model parameters? How much certainty have I got with this prediction? So this comes down to, in terms of what we can say with certainty in terms of the modeling process. I would also say, in terms of translating to patient-specific modeling, there's a lot of thought must go into how do we evaluate the utility of this. And from a clinical perspective, there may be some worry. If we use patient-specific modeling, then maybe the patient can say, but look, you promised to do this, and look, this is what I ended up with. So eventually we can see advantages in this in terms of actually scoring surgery. But before we do this, we must consider that we know so little about the healing process. So in terms of evaluation of all of these methodologies, I think we need to start thinking about how can we collate data post-operatively to look at what has the healing process done after we planned, we executed, we performed, but then what happened downstream. And these are lessons, of course, which are very familiar in the cardiovascular area, and now we hope we'll find some of the relevant data here in this in the airway data. But I would take a step back also, and that is just in terms of, let alone the CFD, but what are the potential of 3D modeling? So one of the great advances in imaging has allowed us to build three-dimensional models. And it may be the case that we should look at what this data is telling us and how we can relate different geometries to different conditions. And I think this is probably an area where there certainly is a potential for machine learning, provided it's given good data. And so that really is, the onus is on us to provide good, well-founded data that we can then be confident of. Because who knows what associations will be found between different geometry patterns and different pathologies ultimately, and different ways of treating. So I would say that let's not rush forward into CFD before we maximize the amount of information we can get just from the three-dimensional geometry and the potential to look at geometry in a three-dimensional way. And then we talk about, well, what does CFD add to all of this? And in my view, it adds significantly, but provided we know the limitations of the CFD. And so I think probably that's where I should stop at this point and listen to hear what you can tell me for the rest of the meeting. So thank you very much indeed.
Thank you very much. It's Dr. Wang Kam from Singapore. So in the last few years, we see so many papers, increasing papers regarding CFD. And then are we able now to make a consensus or statement? So what's the basic criteria? For instance, like a mesh modeling or this quality, because now it's very hard to judge. I often receive such paper for review. And then I really don't know what's the quality, because if you base on the base description, it looks good, and then result looks fantastic, but we don't know whether this is a very artificial or this is truly.
I think that is a very important point, and it's one of the questions which I was alluding to, that I think it's important because there is a wide variety of methods in use. There's a wide variety of boundary conditions in use. I think it's very important at this stage for people who are producing papers to provide some details in terms of what quality checks they've done, what convergence studies they've done, what it is they've actually checked, and what the basic modeling they've used is, so that then this can be checked. It can be checked in terms of, is this reasonable? I mean, if someone says, well, I just used a 500,000 tetrahedral element mesh, right at the start you'd know, well, that's probably not sufficient for many details. But it would depend upon exactly how the mesh was refined and what checks were done. So I think that is essential. I don't think at this point we can say that there is a precise, if you like, formula for everything. I think at the moment I would prefer to say that we bear in mind the level of accuracy that we are hoping to achieve and how we've validated that, what checks we've done. That's my personal view. I'm sure other people may have other opinions.
I think one interesting conversation that would be interesting to have is how accurate the results need to be in order to be clinically relevant. And I'll have some slides on that. So in my mind, there is a basic science perspective that we want to have the greatest mesh density possible to get the exact results. But you can also, in my mind, get clinically relevant results with a lower mesh density. As far as uniformity in the literature, yeah, I agree that's a big deal. It's hard to judge just by reading someone's paper how accurate the results are. I think as reviewers and as writers, we need to do a better job at requesting authors to document precisely what they have done. Maybe that's another topic we can talk about today. It's like what would be the minimum criteria that we should include, or the minimum set of parameters that everybody should include in their papers.
Yeah, Denis Frankito from Duke University in the United States. I just to add to what you guys said, I think one very big issue we have is that a lot of papers have word limit. So you want to provide details, but you have like 3,000 words. How do you manage it? I get my opinion. A forum like this, we need to start thinking about: do we need to have our own journal? If we have our own journal, where we know that people have more word limits, or say you can provide a lot of details, then it's easy to access. We publish in clinical journals. We publish in basic science journals. So these different places, they have different requirements. And if you are publishing to a clinical journal and you want to now provide all your details in your method of how you did the analysis, they're not going to read it. They just want to see the clinical relevance. If you are publishing in a basic science journal and you're providing a lot of clinical information, so these are the problems you're facing right now. That is the reason why when you read a paper, there's uniformity is zero because of the requirement from the journal. I think it's something that we need to bear in mind.